Today we are getting into some math. Oh boy. So, um, your warm-up question is right here. What properties outside of the planet itself determine a planet's average temperature? Okay. So when I say outside of the planet itself, like anything that would be actual property of the planets, you might think, well, like the atmosphere or um I don't know, like how much ice there is or something, right? Like that's on the planet itself. So outside of the planet itself, what do you think determines the average temperature of a planet? Again, I don't necessarily expect you to get all of everything you can think of, but think about it logically, and see what you can come up with. And I'll give you a hint. There are actually three main things, though two of them can sort of be lumped together in one kind of overarching thing if you want to go about it like that. So, uh, give you a bit of time to think about this and put down your stuff. Okay, so the planet, the temperature of the planet. Well, okay, it's a couple things. So the first one, and you should hopefully have this, is that well, it matters how far away the planet is from its star, right? Obviously, like Neptune is a lot colder than the Earth is, so yeah, okay. So the distance between star and planet, that's definitely a factor. However, as you may imagine, if we put the Earth the same distance away from some other star, it would not necessarily have the same temperature as it does right now, and you can kind of imagine why that would be. So, how you describe this is kind of twofold. You could say it's based on the star's luminosity. Okay, so if you just want to say that we or the brightness of the star, the brighter the star, the hotter the planet's going to be, and that's true. So you could either say, um, and and the star's luminosity. That's fine, or luminosity slash brightness. That's fine. Or you could say, um, and the star's temperature and size. Okay, because those two things actually kind of determine its brightness. So it sort of depends on how deep you want to go, right? So in terms of like standard units, right? Again, because here we have distance that'd be measured in meters, temperature is in Kelvin, and size is in meters. Then that's all the way down. Then okay, I guess that's technically the most standard way of describing it. But if you wrote luminosity or brightness, that's not wrong really either. So yeah, either of those. I'll leave it like this, but either one of those is fine. So this is what determines a planet's average temperature. Now, today's point is to actually figure out what that is. Okay, how can we calculate that? And you might think that seems like that would be kind of hard to calculate. But um, notice that from this answer, there's not too many variables that are involved. Again, this is an average, approximate temperature. This whole idea is it's assuming that a planet is like a perfect sphere, meaning that there's no imperfections at all, right? Which is not true. I mean, we have like mountains and oceans and stuff. So it's a perfect sphere. It's a perfectly smooth, 100% non-reflective material, no atmosphere, right? So this is definitely an approximation, and there are some planets that, for example, are very not the temperature that they actually are that you could calculate by this. But it's a start. It gives you some idea, and this can once you kind of get to this, it can start. You can start asking questions about life and how that could happen once you have temperature. So we're going to start with the luminosity equation that we started with all the way back in December. And it was luminosity is the surface area times this sigma constant times temperature to the fourth. Okay, so L was your luminosity. I always do that in watts. A is your surface area in meters squared. Sigma is your Stefan Boltzmann constant, which is 5.67 times 10 to the negative 8. And T is your temperature in Kelvin. Kelvin's capitalized. Okay. So, and this basically tells you, okay, if I have an object that is of this temperature, and it is has a surface area of this, then it is emitting heat as light, as radiation, with this amount of brightness. Okay. Now for stars, you can sort of make this a little bit more specific because stars are spheres. So you can change this to say, well, the brightness of a star. Well, I don't need to say a broad surface area term. I could say, well, what's the surface area of a sphere? 4 pi r squared times sigma times temperature to the fourth. Okay, so we've taken the surface area, given us the surface area of the star, which is a sphere, and then just say, it's the radius of the star and the temperature of the star. So this gets you the brightness of a star. And you can put, for example, if you put in the numbers for the sun, you'll get, I think I went over this before, but here, let's actually do it again. So what is the brightness of the sun? So we have 4 pi times the radius of the sun, which is about 6.96. I just looked this up earlier, so pretty sure that's what it was. And that's squared times 5.67 times 10 to the negative 8 times, that's your temperature of the sun to the fourth. Okay, so what do we get here? 4 pi, okay, we want to square this. So 6.9634 times 10, 8, that, and we want to square that. Okay, I'll be lame and do 4.85. That gonna be to the 17? 3, 6, 9, 12, 17, yep. 17 times 5.67 times 10 to the negative 8 times, okay, 5778 to the fourth. Oh boy, okay, it's not a great number to round. You know what? I'm going to go all the way to here just because I can. Okay, so there's 3, 6, 9, 12, 15. Okay, so that's 1.114577. We got to multiply all this out. So we have this times... I'm actually going to kind of not round the... Here, I'm not rounding. I'm not putting in the rounded value for the r squared. I'm actually just multiplying the full answer of this. Okay, so that's the answer for that. And then we have times the Stefan Boltzmann, so 5.67 times n to the negative 8. That doesn't look right. Hold on. Oh, because I haven't done the 4 pi yet. Okay, right. Okay, I was like, wait a minute. So you know what? Screw. I don't want to. What is your actual answer? So times 4 times. Where's pi? Pi. Hold on. 3, 6, 9, 12, 15, 18. Actually, no, that is about... Yeah, okay. So you get 3.85 times 10, 26 watts. I believe that's right. Let me actually double check this. Make sure I'm doing this correctly. I believe it should be about that number. So let's just type in sun. And we go to... Let's see. They're about... Luminosity. 3.828 times 10 to the 26. And what did I get? 3.85. Okay, yeah, again, rounding, you can see rounding could be a bit of an issue, and again, these numbers are not 100% perfect, but there you go. So yeah, it's about 3.8 times 10 to the 26, so I'll just do that. Um, so this is known as your brightness of the sun. So actually, if we go back to the HR diagram, I believe I have this one? Nope, not that one. Is it this one? Nope, that link's broken. Cool. Nope, not that one. Where's the graph that I want? This is why I should totally plan this out. That's a link that doesn't work. That's a link that, I mean, that can work, but I kind of prefer a different one. Screw it. Okay, let me just do this one. Or no, not that one. This one. Okay, so here was the whole, like, this luminosity scale, though, as we had before, and I mentioned how this was based off of the sun. So 1 on the luminosity scale lines up with wherever the sun is, which I guess in this diagram is probably this one. So what this is saying is this luminosity is compared to the sun. Okay, so just like how we had like Earth masses and solar radii and like even the astronomical unit as the distance between Earth and the sun, now we also have this term here where, and we should probably use the technical, was the non-rounded one, so 3.828 times 10 to the 26. Okay, so in other words, this is known as a solar luminosity. Okay, and so we can compare different stars to this. All right, so for example, stars like if you remember in the HR diagram assignment, one of the stars, the really small one, was TRAPPIST 1. TRAPPIST 1, if we kind of look this up, so it will here. See, there's all these terms here. So see, here's M8V, right? Here's your spectral type. The magnitude, who cares about that? But we also have, yeah, there's distance, how far away it is. But here we go. Luminosity. Okay, so this, you might wonder what are the difference between these two luminosities. The difference here is basically this luminosity says, because it's visual, this is basically how much visible light is it actually emitting compared to the sun, where this is how much total light is it emitting. So yeah, so in this case though, and remember this, so if you remember this circle is, yes, the solar luminosity, the circle with a dot in it is like the symbol for the sun. So that'll if you see what that is, you'll maybe, again, you'll also see R with that. That's the radius of the sun. This is the mass of the sun. So it gives you these numbers here. Bolometric is like all of the light. Okay, so because like there, this star emits, for example, a lot of infrared light. So sure, it emits like very little visible light compared to the sun. I mean, still, that's less than 1,000th of the light of the sun. That's like 1/2000th of the light of the sun. So it's a lot dimmer in that manner. And this is a very small star. And on the other hand, you have like Rigel, which should give you, let's see, Rigel, which is, where's the term I want? Here, luminosity. Well, yeah, 1.2 times 10 to the 5. Okay, so this is 120,000 times brighter than the sun. Okay, so you can see there's a very big range here that you can get with these sort of stars. And so it's a way of comparing it to the sun that helps the things. See, again, these numbers here, it helps to compare. So, how big is the sun? Oh, it's 21 times the mass of the sun. How big is it radius? Oh, it's about 78.9 times the radius of the sun. It's about 120,000 times brighter than the sun. The temperature is an absolute value. Surface gravity is in CGS for some stupid reason. But this also should be compared to this. I'm actually log G. I'm actually not sure how that scale is done here. But you can see we also have, this is how fast it's rotating. So 25 kilometers per second. And also how old it is. So this star is only about 8 million years old. It says only, but well, it is only actually. Anyway, you can see all these sort of terms here. Oh, this is a binary star system? Very interesting. Okay. Oh, wait, it's a... blue supergiant. Hey, whatever. Doesn't matter. Anyway, my point is, so this luminosity term is helpful if you're looking up stars. Oftentimes, a star is written in terms of solar luminosity. It's not going to give you this wattage number. It's going to give you the number compared to this. So if you have a star that's, again, like Rigel, 120,000 times brighter, you want to know how much actual watts it's emitting, then you would take this number and multiply it by 120,000 and get the number you want. So yeah, you can use that in that case here. So this energy is what heats up a planet that would be orbiting the star. However, not all of that energy hits the planet, right? Because a lot of it goes in like another direction. So how do you actually kind of get to this? Well, there's kind of a couple things you can do. And this is about to be kind of a long process that's not really that important, but I want to show it to you anyway, just so you can get an idea of how this works. So the energy of a star, again, is emitted in all directions. It's emitted like a sphere, but we only want to care about the small bit of that actually hits the planet. Okay, so this is actually the most similar thing to this is, remember sound intensity? When we kind of had like, here's your energy output of your sound, and then you divide it by like this kind of spherical shell radius of how far out you are. That is what we're going to do here. Okay, so we're going to say, here's a star, it's emitting this amount of energy, and there's a planet that's a certain distance away from it. How much energy is actually going to be dispersed out to this planet? So just how for sound, we took the energy and divided it by 4 pi r squared, we're going to do the same kind of thing here. So we have our actual luminosity, which I'll just keep that as L, and we're dividing it by 4 pi r squared. Now this is not the same as this r here, the radius of the star. This is sort of the orbit radius, depending on how the distance between the star and the planet. So let me actually write that in there. Orbit. Okay. So we have that in there. This would sort of divide out and give you a number that we actually... That's basically... This is sort of like how the intensity of the sound was like the energy density of the sound. This is sort of like the energy intensity of the sunlight, okay, as it spreads out from its star. However, even though this is how much is spread out at this distance, we only care about, though, how much actually hits the planet. So what we want is actually to take this and to multiply it by how much is actually going to hit the planet. Now, what happens here is it actually doesn't care about the surface area of a planet because, for example, the light does not hit all sides of the planet at once. It hits half the planet at once. So, in other words, we can sort of treat the planet just like a flat disk. You know, haha, flat Earth meme is funny. But you can treat it that way because that's what the sun... Think of it as like the shadow, right? When you have a sphere and you shine a light on it, the shadow is a circle, right? So we care about that circle. That's all we really care about. So this is actually... So we want to actually multiply this by just pi r planet squared. Okay? This actually tells you how much light hits a planet. Okay? That's what that actually tells you. So you're taking the energy output of the star, dividing it by the surface area of this orbit sphere, and you're multiplying it by this is actually the cross-sectional area of the planet. Okay, basically the 2D area of the planet. So this kind of gets you the light. So in other words, this is how much energy actually will hit the planet. So then the question is, okay, how hot is the planet going to be? Now, how this works and how we can figure this out is because any sort of object wants to be at a steady temperature, right? If you give something energy, it will warm itself up until it, reaches its own stable temperature. So we talked about this again back in December, but the idea is that as this light hits a planet, it's going to heat up. Now, as the planet heats up, again, it is an object that has a surface area and a temperature. It is going to be emitting its own energy, not as like visible light because a planet's not that hot, but as infrared light. So as the planet heats up with its temperature increases. That means the planet is sort of balancing that by emitting more light back out into the universe. And it wants to be at a balance. It wants to be at what is known as thermal equilibrium. In other words, it's saying the energy coming in, which is this, should equal the energy going out. Okay, we need this sort of balance. And that energy going out, so I'll say equals E in. The energy going out is, again, this luminosity formula, but now for the planet. So, A. However, again, it's for the planet. So, again, planets are spheres. So, we actually want 4 pi r planet squared times sigma times t. I'm going to label this as EQ for now, and I'll get back to that in a second, why it's called that, to the 4th. And so this is E out. And the whole point of this is to say that E in must equal E out. Now, this looks terrible, okay? This looks really terrible. So you're thinking we have L star, and also, as you may think, like, hold on. I'm actually going to do something that might look even more terrible. Like, why would you do this? But I'm actually going to replace L with this. And you might be thinking, oh god, no, why are you doing this? But there is actually a reason. It actually makes things easier, believe it or not. So we have 4 pi r star squared times sigma times t star to the 4th. All of that divided by 4 pi r orbit squared. Now, all of that is now times, so because it's times, I'm just going to put it in right here. Pi r, let me get rid of the, here. Planet squared. And that then equals 4 pi r planet squared sigma t eq to the 4th. Okay, that looks incredibly gross, but there are some things that actually make this not so terrible. For one, notice we have 4 pi divided by 4 pi. Okay, so we can just sort of get rid of those 4 pi's. So we have r star squared sigma t star to the 4th. We still have this pi, and this r planet squared divided by r orbit squared equals, we still have this 4 pi like that. Okay, so we still have that, but let's see, we have sigma here and sigma here. Okay, so we can actually just cancel those. So, let me just copy this over and then just go boop and boop. Okay, so we have that, so we can get rid of the sigmas. Now we have pi r planet squared and pi r planet squared. Okay, now there's still a 4 here, but we can deal with that in a bit. So we can actually divide out pi planet squared with pi planet squared. This looks a little bit more reasonable now. So let's sort of let me switch the order of this and let me divide by 4. So we have t eq to the 4th equals r star squared. T star to the 4th divided by 4 r orbit squared. Now, everything here is squared. Okay, well, these are squared and the temperature is to the 4th. So we can square root everything, okay? And also we have 4, which square root becomes to 2. So this becomes t eq squared equals r star e star squared divided by 2 r orbit, okay? But we still have temperature squared, so I don't really want to deal with that. So I can square root again, which means I can sort of pull the t star out in front, and then I have to put everything else in the square root. So I end up getting t eq equals T star square root of R star divided by 2R orbit. There you go. So we got from this terrible, disgusting looking mess, but a lot of it just cancels out, and just with a little bit of shifting and square rooting, you get that. That's pretty simple. So what does this say? Okay, so let me get through everything. So T star is surface temperature of the star. Okay, easy enough. R star, oh, let me clarify in Kelvin, is radius of star in meters. Our orbit is radius of planet's orbit in meters. And so what is TEQ? So TEQ is what is known as the equilibrium temperature. Okay. Which is, aka, this is basically the approximate average surface temperature of the planet. Okay, again, it's an average and it's approximate. It's not perfect, but this is a way of calculating this. This is basically saying if the planet was perfect, okay, it was a perfect sphere, no atmosphere, the material's all the same, it's non-reflective, all that stuff, this is what you would get. So what does this look like? Let's actually plug in a number here. So let's actually find what is the TEQ of Earth. What is this? Okay, so let's see the numbers we want. We need the temperature of the star, in this case the sun, which is the surface temperature, so that's 5778. Okay, then we need the radius of the star, which is 6.96 times 10 to the 8, divided by 2 times the orbit of the radius. That's it's 1.496 times 10 to the 11. Okay, that's the radius of the orbit of the Earth. So let's see what we get here. First, let's multiply this by 2. So we have 2 times 1.496. Okay, so that becomes 2.992. Actually, wait, you know what? Hold on. Should save my work here. 2.992. Then I want to divide this here. So I'm going to do okay, and then I want to flip this, so there you go. So my number is going to be this within square root. Okay, so there's my number in the square roots. Then I want to square root that, and I get this. So TEQ Earth equals 5778. 278.677. Now, you might think, okay, is that accurate to like the temperature of the Earth? I don't know, right? So let's figure out what that is in the other temperature scales. So to get from Kelvin to Celsius, you subtract 273. So we get 5.677. Is that degrees? Yeah, it's degrees. Degrees Celsius. And to get to Fahrenheit, you multiply by 1.8, and you add 32. So, does that seem reasonable for the average temperature of the Earth? You might think, well, that seems a little cold, but it's not like it's like, -40, right? That'd be probably too cold. But this is actually kind of reasonable, because think about this. This is average night and day, summer and winter, North Pole to equator to South Pole. Okay? That's actually not that wrong. And so I believe the actual average temperature of the Earth is about, I think it's like 59 Fahrenheit. So this is pretty dang close, all things considered. Okay. So again, considering what honestly fairly simple numbers we're working here with which is just temperature of the sun, radius of the sun, orbital average orbital radius. Again, this number does vary a bit, right, as the Earth goes around the sun. And again, this is averaging all seasons, all climates, all day and night, all of that. This is pretty good, right? Considering how simple this formula is. It's a pretty simple, algebra formula. So we can get pretty good, and get a temperature here that actually makes sense. So this is a surprisingly powerful tool. Beyond what you would expect, considering this is not an incredibly complex formula. Again, this is sort of what is often referred to as a first order approximation. In other words, basically it's using sort of the simplest terms to get at least an okay approximation, but as you may imagine, you can add more terms in here to make this more accurate. For example, the Earth is not perfectly absorbing, right? It reflects some light. This is actually an issue for climate change because ice reflects a lot of light, but as we melt the ice, we end up absorbing more light, which means we get hotter. So, anyway, but there is a factor that involves in here that you could add in on this. You could also add a factor in that talks about like the atmosphere and how that works, right? So you can add complexity onto this. But you can see how this is actually not so bad. So, and you could do this with any planet around any star, as long as you know the star's temperature, its radius, and its orbit. The orbital distance between the planet and the star. And that's it. And that's really powerful. Because you can calculate a lot of stuff that you can just sort of immediately sort of dismiss it in hand or whatever. So, for example, let's look at... let's go back to the TRAPPIST-1 system. You know what? Let me pick a random planet. Let's do 1D. So this is a planet in the TRAPPIST-1 system, okay? And what do we have? We have, for these kind of planets here, whenever you get a distance, you want to probably use the semi-major axis, because that's sort of your average distance in a sense. So we have that, and then those are numbers of the planet. Do I have numbers for the star? I mean, I can just find it. So TRAPPIST-1. TRAPPIST-1. Okay. So let's find what is our equilibrium temperature for TRAPPIST-1D. Okay. So what are the numbers we need? We need the temperature of the star, which we have, let's see, temperature of the star. Temperature, 2,511 Kelvin. Okay, and then we want the radius of the star. Radius. Okay, so it's 0.121 times the radius of the sun. Okay. So, let me just... Okay. Yeah, so we have to multiply this out. So in other words, it's 0.121 times this radius. So let's find what that is. So 0.121 times 6.96 times 10.8. Okay, so it's 8.4216 times 10 to the 7 meters. And then we want the orbital distance, which in this case you can use a semi-major axis, which we found was... Okay, I'll do 0.2228 or 0.02228. Okay, so it's 0.02228 AU. So we have to therefore convert this to meters. 1.496 times 10 to the 11 times 0.02228. Okay, so this is... I'll just use 3.333. Okay, so that's 10 to the 9? Yes. Okay, so we have those numbers. Let's plug them into the formula. So T EQ equals temperature of the star 2511 times the, we want the radius 8.4216 times 10 to the 7 divided by 2 times 3.333 times 10 to the 9. Okay. So, let's multiply this by 2 first. Yeah, so that's not surprising. .4216 times 10 to the 7. Okay, divided by 6.666 times 10 to 9. Then you have to divide that. So and then you want to flip it. Okay, so we get this all around here, actually. It's good to be. It's often nice to be kind of round, very conservatively in this sense, just to always have the number as like as precise as you can. That's within reason. So here's my number there, and now I want to square root that. Okay, I'll do 0.1124 in this case because it's not so bad. Okay, times 2511, and I get 282.2316. That 2316, yeah. So this planet, and again, you might not be able to tell immediately how this is compared to the Earth, but here's the Earth, 278 Kelvin. This is 282 Kelvin. So this planet is a little bit hotter than the Earth. Okay, but let's actually convert to actually make sure what we know the number is. So we want to subtract by 273 to get in Celsius. So that's 9.316 degrees Celsius. 0.8 plus 32. So we get about, well, 1.6 or 6.1? No, 6.2. So it's a little bit hotter than the Earth, on average. This planet is very, and this is very interesting because again, remember this star was the one that was really dim, right? It was like 1/2000th of the brightness of the sun. So it's a very dim planet or a very dim star. So, and again, it's also like less than half as hot on the surface, right? Again, our sun's over 5,000. But notice this planet is very close to its star. Okay, and I think actually if you look at the, let's see, yeah, orbital period, that's days. Okay, a day, right? So this planet goes all the way around its star in 4 days. For comparison, Mercury is 88 days. So this to show that like this planet is a little bit hotter than the Earth, and it orbits its star in 4 days. So that's how dim this star is, and that's how close the planet is. And also, what's kind of crazy is that again, this is 1D. The naming scheme for planets or other stars is again, this is the star name, and then you add in a letter at the end to denote the planet. So there is no A for some reason. I think A is just that A is the star. So the first planet around a star is always B. So this is the third planet around its star, and it orbits in only 4 days. Okay, so this points out to again why I've said that like the TRAPPIST-1 system is very interesting because, do we have like a good table? Okay, yeah, here. So this is the one we looked at was D. That's a very small planet, actually. Interesting. Okay. Anyway, yeah, it's interesting, kind of a small planet. Okay, but you can see these planets here. So, and these are actually in order. They're actually labeled in order of discovery, but these are all discovered at once, so they just labeled them in order. So, there's one of the first one orbits in 1.5 days, then about 2.5 days. Then this is the one in 4 days, which we just looked at. Then this is orbits in 6 days. This one in 9 in the 5th days. This is like 12 1/3 days. This is in 18, in 3/4 days. So we have 7 planets that are all orbiting within like, less than 20 days of its star. So, and again, if you look at the 7 major axis, 0.01, 01, 02, 02, 03, 04, 06, right? This is incredibly close, because again, Mercury is like 0.3, okay? So, this is ridiculous. And also, these planets are all interesting because they're like Earth-ish. Like these, this is, again, this symbol is a symbol for Earth. So again, Earth mass. So this is a little tiny bit bigger, a little bit more bigger. This one's actually about Mercury size, I think, based on at least the mass numbers. Well, I don't know. The radius, though, is different. So anyway, you can see that like these are all fairly close to the Earth in various terms. So we have 7 Earth-ish planets that are all within, really close numbers for their stars. And then, oh yes, you can also see. Yeah, so here's the equilibrium temperature that we talked about. So C282. That's what we calculated, right? So this one that's closest in, this is like assuming atmospheres and stuff like that. But here's the basic one, 391 Kelvin. So this closest planet would be over 245 degrees Fahrenheit. There's probably no life there, right? This one, over 140 degrees Fahrenheit. Also probably no life there. But this one, 48. That's not so bad. This one, negative 16. Yeah, that's pretty cold. Negative 73, that's right. Negative 109, negative 150. You can see the range of this here and see how this all works. I think you also see the gravity. This is all gravity compared to the Earth, which is kind of interesting to see. So the planet that we just looked at here, it actually has less than half the gravity of the Earth, so it's kind of neat. All of these are actually less than gravity of Earth. Here's a whole orbital resonance. I'm not going to get into this. This is really complicated. And stuff there. And so you can see... Oh, okay. This is not like actually how far apart they are, but this is sort of a show of comparison where that this is the distance between the Earth and the Moon. So whatever this distance is compared to the distance between the star and their planets. Okay, so this is B, C, D, E, F, G, H, and again Mercury's way off the scale further away. So yeah, this is a very interesting star system, and there's a bunch of stuff which could get into this that's very interesting. Hence why this is one that's well known and talked about a lot. But again, my point is that this formula here, this here is very powerful considering it's not really that complicated, and again, the numbers that you use are not like the most pleasant numbers because they're kind of large and not great, but it's still pretty neat that you can approximate the temperature of a planet just from knowing 3 fairly simple terms to know. So I don't know, I think that's just so cool. And we're going to kind of work more with this in terms of like other planets and talking about life and stuff going forward. But for now, let's get to the wrap-up question. Okay. So if the sun was twice as large as it is now, what would Earth's equilibrium temperature be? Okay. So again, think about the math here we did to get to this answer here. So I want you to then, okay, what if instead the radius was twice as big? How would these numbers be different? And you can calculate this all the way out again, like I did here, or think about this a bit. There is a way to sort of cheat the system and do a little bit of a shortcut. So think about it. All you're changing, by the way, is the radius of the sun. You're not changing the distance or the temperature. So you can come up with and then come back here. All right. So I'm going to show you the shortcut way. So the shortcut way is that all of these numbers are going to be the same, except this one is 2 times bigger. Okay, so think about what we have here. We have it's the temperature of the sun, which is, a number. What the heck? Must have hit something I didn't mean to hit there. Sus. No. There we go. And then we have times the radius of the sun divided by 2 times r. I guess I'll just say that. Okay, so those are the, and again, if you plug in the right numbers, you'll get the answer we normally have. So this equals, well, TEQ Earth. We have that. Okay, so, but what we want, though, is to instead say, okay, what if I instead have twice the radius of the sun? Now, everything else is the same, so what you can do is, well, what if I sort of factor this 2 out of the square root? Okay, so in other words, what I could do is I could say well, this actually wouldn't be TEQ Earth, but this is TEQ, I'll say New Earth. I don't know. I don't know why I did that. And so then I have TEQ New Earth. So I have to take the square root with it. So square root of 2. But then it's times. Since I've taken the 2 out, it's just times everything else. But that also, this here just equals TEQ Earth, right? I've just factored out the 2 from within the square root, and all the rest of the numbers are still the same as before. So in other words, this new equilibrium temperature, which I'm just going to abbreviate to TEQNE because I'm lazy, it's going to be square root of 2 times what the temperature was before. Now keep in mind, it's the temperature in Kelvin. So it's going to be square root of 2 times 278.67? Yeah, okay, 278. So in other words, 1.414 times 278.677. So we want square root of 2 times 278.677. 394.1. Which is 121.1 Celsius, which is 250 Fahrenheit. So, if the sun were to double in size, the Earth would all of a sudden jump from an average temperature of about, 40, 50 Fahrenheit to 250 Fahrenheit. So you can see kind of how the scale of this is rather interesting how this can work. So, granted, to be fair, it actually would be worse than this, because if you were to double the radius of the sun, you would also change the temperature of the sun. It's the surface temperature, actually, so the temperature actually would probably be a little bit less, but not enough to, counterbalance this and make this actually, livable. So, this is also why, when the sun will start to go into its red giant phase, sure, eventually that we think the sun will actually grow large enough to literally swallow the Earth in terms of its orbit. But before it does that, because this radius term is growing by a lot, while the temperature will be shrinking a little bit, this number will still get way bigger to the point where, you get this, and life is not possible. So, yeah. But you can see kind of how that works there. So, you have actually homework questions, like normal homework questions, that are based off of dealing with this term. So the first question is, you have brightest star is this thing here. Surface temperature is 53,000 Kelvin, and its radius is 28.8 times that of the sun. So what I first want you to do is calculate the luminosity of the star in watts. Okay, so that goes all the way back to what we did with the sun, which was right here. Yeah, so when we calculated this from this stuff here, again, you're going to have to multiply, well, the temperature I give you just normally, but in terms of the radius of the star, you'll have to multiply, by the radius of the sun, which you can look up, or just use the number there. And then calculate the luminosity of the star in solar luminosities, so whatever number you get for A, you're going to divide that by the wattage of just the sun to find out basically how many suns it would take to be this bright. Then if the Earth was orbiting this star instead of the sun, same distance, how hot would it be? So you're going to find the equilibrium temperature, this time with the temperature of this new star, the radius of this new star, but the same distance. You'll find the number is very large. And next question is, how far away must the Earth be for it to have the same temperature as it does now? So in this case, you're basically saying, okay, this temperature is the same. It's going to be the same number here, but this equation is going to equal the new temperature of the star times this new radius of the star, and you're solving for our orbit. And your answer, by the way, that you'll get for our orbit is in meters, and then I want you to solve an AU, so you're going to divide by this number here at the end of your answer in meters. It's also a very large number. So, yeah. Now, number 2 seems like a lot of work, but it's actually fairly quick. Should be 677, right? 78.6. Yeah, whatever. Not like it matters that much. So if you have planets just orbiting our sun, there is a shortcut because all of these numbers are the same, right? T sun is the same, our sun is the same because it's the sun. So the only number that actually changes between planets is just this our orbit distance. So a shortcut you can do is basically take this number and divide it by the square root of the planet's orbital radius. Okay, so in AU. So for example, I don't know, what is it? Mercury planet orbital radius. Okay, so 0.387 AU. You're going to want to use the semi-major axis for all of these, by the way. So what you would do is take 278.667 and divide by the square root of 0.367, and that's your equilibrium temperature for Mercury. And repeat it for Venus, Mars, Jupiter, blah, blah, blah. And you can look up the numbers for these. And again, convert the answer to Fahrenheit just because it's more helpful for you to sort of gauge the numbers. And so then what you'll find is that if you look at the actual temperatures, you'll notice that Venus is like way hotter than what you calculated. All the others will be fairly close. I think Mercury's off by a bit, but it's like not ridiculous. But Venus is like completely off. It's like not anywhere near close to what it actually is. So I want you to then think about, okay, why? What's different about Venus compared to other planets, and like why would Venus be like way hotter than it's quote unquote supposed to be? So I want you to kind of think about that and kind of answer the question there. So yeah, and this will sort of segue into tomorrow, where we will talk in detail about each of the planets and get a little bit more info about them. So that's kind of the main thing to focus on tomorrow. So see what you do with this stuff. Again, a little bit more mathy thing today, but that's how it is. And personally, I really like this because it's an equation that's ultimately way simpler than you might think it would be. Because again, if I asked you, hey, we can use physics to calculate estimate the temperature of other planets, you'd probably think like, oh, that's something like insanely ridiculously complicated with stupid calculus or whatever. But no, not really. It's actually just fairly simple algebra formula. So yeah, there you go.